Okay, AP Cactus AB, Unit 7, Day 6, Part 2 of the pretest. So we can do all the optimization stuff now. So what is the algorithm for solving an optimization problem? Well, one, you need an equation for what you want to optimize, right? A lot of times you use geometry and whatever. You want it in one variable. So there's usually some other condition that you can use to eventually get it in one variable. Then you want to take the derivative and set it equal to 0, undefined. And you want to find the critical points, and you want to find the endpoints. And then number 3, you want to plug your critical points and endpoints into the original function. Right, original function. Get something like this. You got your endpoints and your critical points. And you plug them into the original function, you get values, right? So, and then you find the max min. Now, if you don't have endpoints, then you can't use extreme value theorem. So what you could try and do is use first derivative test for relative extrema, find the relative max and min, okay? If there's only one, then we can maybe conclude that it's the absolute max or min. But that's only going to work if only one critical point. For instance, your line check might look like this. You have a critical point, and you get a positive, negative, and it's going up and it's going down. So this is a relative max, but in this case, it's going to be an absolute max also. I would not recommend using this approach unless you have to use the approach, okay? So that's the strategy. Okay, number 12, rectangular poster contains 50 square inches of printing with a 4-inch margin at the top and bottom, 2-inch margin at the sides. What overall dimensions will minimize the paper used? Okay, so should probably draw a picture. Poster has a border, and the area inside the poster has to be 50 square inches. Top and bottom is 4-inch margin. Left and right is 2-inch margin. And so we should probably create some variables. Like this could be x, that could be y. This could be x plus 4. This could be y plus, x plus 4. And this would be y plus 8. There to there. So we're trying to minimize the paper used, which would include all of it, including the borders and everything. So we got to find the area. The area would be base times height, x plus 4, times y plus 8. And then we want to get in terms of one variable. So this other restriction is the area inside has to be xy. It has to equal 50 square inches. So then you could do y equals 50 over x, or x equals 50 over y. And you could put things and use different letters of meaning, put them in different places. So we're going to plug that in. So x plus 4, 50 over x plus 8. So now we have our formula for the area that we're trying to optimize, minimize, in terms of one variable. It's probably good to go ahead and multiply this all out. 50 plus 8x plus 200 over x plus 32. We could simplify it. 8x plus 200, probably x to the negative 1 for derivative purposes. So there's our area formula. I'm going to take the derivative of it, 8 minus 200 x to the negative 2. And so then that's going to be 8 minus 200 over x squared equals 0 undefined. And so I personally don't like to cross multiply because you potentially lose solutions. I think you would here. So I'm going to give a least common denominator. 8x squared minus 200 over x squared equals 0 undefined. So undefined comes from bottom x equals 0, which is balance issue, which you would have missed if you cross multiplied. 0 comes from the top. So that's going to be x squared equals 200 over 8, which is 25. I'm going to take the square root of both sides, plus or minus, plus or minus. These are your critical points. Now we've got to figure out what the endpoints are. Could x be 0? No, it can't be, because then you wouldn't have any area inside. It says it has to have 50 square inches there. It can't be 0. What's the biggest y could be? What's the smallest? Y could go towards 0 but can't become 0. As y goes to 0, x equals 50 over y, x blows up. So essentially it goes to infinity. So we don't have endpoints. We can't do extreme value theorem. We could do something kind of like extreme value theorem, but it's not extreme value theorem. So we're probably going to have to try and do what I was saying, use a first derivative test. Now, if you were to try and kind of organize it like extreme value theorem, you just can't call it that for justification purposes. I mean, you could figure out what's going on. So we're going to take the limit as x goes to 0, and then we have positive 5, negative 5 is not possible. And the limit as x goes to infinity, what happens is we go to 0 here, and we could even plug it into this one. This goes to 0, and then this blows up. It goes to positive infinity. The area goes to positive infinity. If you plug 5 in, you're going to get 9 times 18, which is 90, 162. If you go to infinity, this term goes to 0, that term blows up, and the whole area goes to infinity. So from this, we could tell this is the min, right? You just can't say they used extreme value theorem. I mean, you could try and explain this in the words, which you would have to. So the other option is first derivative test, and that's where we're looking for relative maxes min. So we do a line check. You still have to find your critical points, test a value. X equals 6 is going to be, where's the derivative right here? Here's the derivative. 6, 200, I don't know. I don't think I'm going to do 6. I'm going to do, can I do 0? Let's do 1. It's negative, negative, positive, positive, increasing, decreasing, increasing, increasing, decreasing, increasing, relative max, relative min. Now, in general, from this, you can't determine the absolute max or min because this keeps going up. It depends on the endpoints, and we don't have endpoints, so we're kind of stuck. But we do know that x has to be greater than 0, right? So we can throw that out. X has to be greater than 0. It can't have a negative length. With that, now we're like, oh, well, this is the only relative min. That's for sure the lowest point, absolute min. Okay, now to justify this, which is what I need you to do, so you really only want to do this when you absolutely have to. So here's the answer. Now, they didn't ask for the maximum, and if you did it this way, you would still have to plug this back into the original function to find out what the maximum is. I mean, if you found it, or the minimum, if you found it, you could write it, but you don't have to, I guess, but it's just good practice. The minimum area is 162 inches squared units, and occurs when the width I don't want to say x because I made x up. The width of, let's see, the width of the picture. The width is, the whole width is 9 inches. And the height is, it's going to be the y value. 18 plus 8 is 26 inches. So, I mean, that's the, what is it? Shoot. Did I mess up? Okay. No, that is the answer right there, is that 18. So it's 18. By the way, there's the answer. There's a 9. Okay. So that's just the answer. Okay. But how? We could say there is a relative minimum there by the first derivative test for relative extrema. Okay, cool. That's the name of it. How does it work? Since A prime is negative on 0 to 5 and A prime is positive on 5 to infinity. Okay, cool. Well, why is the relative min and absolute min? And since it is the only relative extrema, it must also be an absolute minimum. This is why you don't want to use this. If you don't have to, you don't want to do this. It's hard to explain. It's hard to defend. And it generally doesn't work. So we only want to use it if we absolutely have to. Okay, next problem is a problem we've seen a couple times. Problems like this. Hillary is 2 miles offshore in a boat and wishes to reach a coastal village 6 miles down a straight shoreline from the point nearest to the boat. She can row 2 miles an hour and walk 5 miles per hour. Where should she land her boat to reach the village in the least amount of time? We need a picture of this. She's 2 miles offshore. So here's the shore, right? And she's 2 miles offshore in a boat. So 2 miles is this distance, right? Wish to reach a coastal village 6 miles down. So 6 miles down is the village, right? So what's going to happen is she's going to row to a certain point and then walk the rest of the way. Whatever is most efficient, I guess. She can row 2 miles per hour. She can walk 5 miles per hour. Often it's harder to row than to just walk on ground. Okay. So this is rowing. This is walking. So we need to come up with a variable. And I'm telling you, this is the best place to put it. If they haven't given it to you, this is the best place. It's the least messy place. So then this distance is 6 minus x. And this one, using Pythagorean theorem, is the square root of x squared plus 4. So then we need to use the relationship d equals rt, distance equals rate times time, time equals distance over rate, least amount of time. We need a time equation. So your time equation is distance rowing, square root of x squared plus 4, over rate rowing, 2, plus distance walking over rate walking. So there's your time equations in one variable. So you might want to rewrite it before you take the derivative in something a little easier to take derivative of. This is 1/2 power, 6/5 minus 1/5 x. So if we take the derivative, t prime equals 1/4 x squared plus 4 to the negative 1/2 multiplied by the derivative of what's inside, Derivative 6/5 is 0. Derivative negative 1/5 x is negative 1/5. And we're going to set equal to 0 undefined. So I would rewrite this a little nicer. T prime equals 1 over 2 square root of x squared plus 4 minus 1/5. I would combine these into a single fraction. So this is going to be 5 minus 2 squared root of x squared plus 4 over, oh shoot, I missed, oh, there's an x here, x, 5x. So least common denominator, set equals 0 undefined. Now, undefineds come from this guy, x equals plus or minus 2I, which we're going to throw out, but you should write down. And then 0 comes from this guy. So that's going to be 5x equals 2 square root of x squared plus 4. We're going to square both sides. You get 25x squared equals 4x squared plus 16. I think so far we're on the right track. So we have 21x squared. And divide by 21. We're going to take the square root of both sides, plus or minus. So you get 4 over square root of 21 and negative 4 over square root of 21. These are your critical points. Now, the endpoints, what are the possible values for x as far as endpoints go? Could x be 0? Sure. She could row directly to the shore, walk the whole way, the rest of the way. What's the smallest x be? Well, the biggest x would be 6. She's not going to go past the town and walk backwards with negative distance that makes up time. Like, one, you already know the least amount of time she shouldn't go beyond her thing, you know. She shouldn't go backwards, right? That's why x can be negative. So let's create a table. Let's use EVT for sure, right? Plug it into time. Okay, and then so you have negative 4 over the square root of 21. Then you got 0, and then you get positive 4 over the square root of 21. And then you got 6. So we're not going to bother calculating any critical points that are outside the endpoints. You can if you want, but they're just not going to make sense. Plug 0 in here. Square root of 4 is 2 over 2 is 1 plus 6/5 equals 2 and 1/5, or 2.2. Okay. This one's kind of ugly. You're going to square it, so you're going to get square root of 16 over 21 plus 4 over 2 plus 6 minus 4 on the square root of 21 minus 5. Let's see if we can clean this up. Least common denominator would be 21, 21. That'd be 84. Ooh, it's going to be square root of 100. Square root of 100 over square root of 21 over 2. This is going to be 6/5 minus 4 over 5 square root of 21. This is ugly. So that's going to be 10 divided by 2 is 5. So you get 5 over the square root of 21 minus 6/5 minus 4 over 5 square root of 21. I guess we try and combine these together. 5, 25. Minus 4 is 21 over the square root of 21 minus 6/5. Now let's just try and estimate this. Square root of 21 is between 16 and 25 is between 4 and 5. It's a little closer to 5. So I would say maybe it's like 4.6. How many of those can we fit into 21? 4.5 or so. Maybe about 4.5 minus 1.2 is about 3.3. So I don't know. Now let's calculate the last one. 6 is the square root of 40 over 2 minus 0. You take 4 out of that. So that's going to be the square root of 10, which is about 3.1 or something like that. These are really close to each other. Okay, so I mean those are pretty close. I think this is where I would let you use a calculator if I give you something this gross. So this one actually should have been 2.117. So I messed something up in my estimates. And this one is 3.162. So that one's pretty close. But this one, we're looking for the minimum. The minimum, so this is the minimum right here. Okay. So we're going to say, and I guess that's one benefit to the first derivative test is that you don't actually have to calculate the output values if things work out just right, which you could do on here, but it'd be a lot harder to defend. So we're going to say the minimum time. I don't even. Minimum time is 2.117 hours when she rows 4 over the square root of 21 miles down the shore by extreme value theorem. Checking endpoints and critical points. So that's justification. I want justification on these. Critical points. I start writing the words I'm saying as I'm trying to write other words. Okay, there you go. Okay, this one is 10 by 16 piece of cardboard is cut as shown. Shaded pieces are cut and folded into the box. Find formula for the volume of the box entry. So this is like we've done a couple box problems like this. This box has a lid, but it's different than the optimization box we're doing that where the top lid is just like the bottom base. So this one's a little different. When you create it, it looks like this, and the lid is just a flat piece like that. So let's see. So we're going to use X for the cuts. It says 10 by 16. So 10. So the dimensions here are going to be 10 minus 2X. And this one's going to be, if this is 16, this one's a little trickier. These are the same. These two are the same, right? So if we said 16 minus 2X, I'll give you what's left, and we're going to divide it evenly. So it's going to be 8 minus X for that dimension. And then the height's just X. So the volume is length times width times height is 10 minus 2X times 8 minus X times X. And we probably want to multiply that out because that'll make the derivatives easier. So I'm going to FOIL this. So that's going to be 80 minus 10x minus 16x plus 2x squared. And then we'll distribute again now. That's going to be what, 70? Did I make a mistake here? That should be an x. So it's going to be minus what, 26x? Yeah, okay. I could write in standard form too. 2x cubed minus 26x squared plus 80x. Okay, no calculus yet. Now here's comes kind of analyze V prime to determine the cut size that maximizes the volume of the box. So V prime equals 6x squared minus 52x plus 80 set equal to 0 undefined. Let's see if we can factor this. We can take a 2 out. 3x squared minus 26x plus 40 And we could try and factor this 3x and 1x. There's not a whole lot of options there. Two numbers that multiply together 40, so we get negative 26. 2 and 20, 2 and 20, 20 and 2, negative, negative. Perfect. Set it equals 0 and define. Write that in your work. So x equals 20 thirds and x equals 2 are your critical points. And then what's the smallest x could be? X could be like the whole side, I guess, right? I mean, you could just, you're throwing away the pieces of cardboard you cut out, so you could just throw away a ton. So it's either going to be 5, right? 5 and 5. Or in this case right here, they could they both be 8? 8 and 8. But whichever one's smaller is the more constricting one. So it's going to be, they could be 0. And then the box would just be completely flat. And they could go all the way up to 5 because then they run out of space on this side. If you keep going past that, it doesn't make sense. You have negative cut lengths, negative area, whatever. So those are your endpoints. So we're going to create a table, preferably, because we do have endpoints, continue function. Why would you do it any other way? 0. 20 thirds is 6 and 2 thirds. So we have 2, we have 20 thirds. Oh, actually, we have 5, and then we have 20 thirds is outside of the endpoint. So we're not going to bother calculating it. We're going to plug it into volume. I like the factor versions. I feel like it makes it work a little easier. So if you plug 0 in here, it's going to be 10 times 8 times 0 is 0. If you plug 2 in, it's going to be 6 times 6 times 2 is 72. Plug 5 in, it's going to be 0 times 3 times 5 is 0. So here's your max. And we didn't have to do anything weird. We just used extreme value theorem. So we're going to say the maximum volume of the box is 72 inches cubed when the cut size x equals 2 inches. Got to use units. How? By extreme value theorem. Okay, well, how does that work? By checking endpoints and critical points. All right, there you go. Now you could pull it off, I think, with first derivative test, but you still got to use the endpoints, and then the explanation is just horrible. So I wouldn't recommend it. All right, here's a problem that kind of looks like one of those optimization problems. Says a wire length 12 inches can be bent into a circle, bent into a square, or cut into 2 pieces that make both a circle and a square. How much wire should be used if the circle and the total area enclosed the figures is to be maximized or minimized? It's the same work either way. So I would draw a picture. You have a circle with a radius r, and you have a square with equal sides s. We're trying to maximize the area. So the area is going to be the area of the circle plus the area of the square. So it's going to be pi r squared plus side squared. Now we really want to get this in terms of one variable. So it's the length of the wire, the perimeter, that's 12, which equals 2 pi r plus 4 s's. So now we can solve for s or r. I don't really know which one looks much easier, but I guess I will solve for s in terms of r. That looks a little better that way, a little bit. Little less fractions. So 4s equals 12 minus 2 pi r divided by 4. That's going to be 3 minus 1/2 pi r. And we're going to plug it into this equation up here to get our area formula in terms of one variable, pi r squared plus 3 minus 1/2 pi r squared. Probably should go ahead and multiply that out. So we get pi r squared plus 9 minus 3/2, that's 3 pi r plus 1/4 pi squared r squared. We haven't done any calculus yet. This is geometry and algebra. Okay, I think we're ready. A prime equals 2 pi r minus 3 pi plus 1/2 pi squared r. I'm going to set this equals 0 undefined. Find our critical points in terms of r. So we can factor the r out. Be 2 pi plus pi squared over 2. Move the 3 pi to the other side. Divide by this. Lots of pi's, lots of pi's. We could also make it cleaner so it doesn't have complex fractions. Multiply both sides by 2. Right? So r equals 6 pi over 4 pi plus pi squared. Hey, we could divide a pi out of the top and bottom. That makes it a little nicer. So there's your critical point. Oh, that was a bit hard. It looks a little ugly. That's fine. Can we find endpoints? Hopefully we can find endpoints. So what are the endpoints? What's the smallest r could be? R could be 0, and we give all the wire to the square, right? The other extreme is we use no wire for the square and use it all for the circle. So if we use it all for the circle, that means that sides would be 0 for the square, and we would get 3 equals pi over 2r. So r equals 6 over pi. 6 over pi is the other endpoint. So these are your endpoints. So we're going to make a table. Even though this is slightly ugly, it's still going to be better to make the table. And I'm going to write down this factored version because I just feel like it'll break the work down. And also, these are the sides of our square. Now, it says how much wire should be used for the circle. So I guess we're looking for the circumference of the circle by the time we're done, which is just 2 pi r. But our endpoints are 0, 6 over 4 plus pi, and 6 over pi. Now, I'm assuming this is between those, and it should be, because it's a bigger denominator and it's positive, so it should be between 0 and 6 over pi. It's bigger than 0, it's smaller than 6 over pi. Now, we're going to plug these in. 0 in for r gives you 9. Okay, that worked out pretty nice. This one's going to be horrible. And this is where, for sure, let's just use a calculator. But on the test, don't expect me to give you a calculator because I might just give you one that's just not so ugly. I mean, but we're going to use a calculator today. And this one, I think, this one might be more reasonable. It's going to be 36 over pi squared plus 3 minus 1/2 pi times 6 over pi. This one cleans up a little better. And this is supposed to be squared also. The pi's cancel, that gives you 3, that becomes 0. So the answer is just 36 over pi. That one's pretty doable, which is about 12. Now on your calculator, this is 5.041 or 5.042. I mean, I think, if we tried, we could maybe estimate that, and it doesn't seem anywhere close to these, so it seems good. But we're trying to maximize the area on one, So this would be your max, and they're trying to minimize the same work with max and min. This is the min. Same work. We don't need to do anything over again. So A says the maximum area is 36 over pi. What are the units? Inches squared when now this is the extreme case where we used all the wire for our when all the wire 12 inches is used for a circle, none for the square by extreme value theorem. Checking endpoints and critical points. All right, B, the minimum area is 5.041 inches squared when, and I guess this is where we need to plug this in 2 pi r. So it's going to be 2 pi r times that. So it's just going to be 12 pi over 4 plus pi inches of wire is used for the circle by the extreme value theorem. Explain how it works. Checking endpoints and critical points. Ooh, that was a bit messy. All right. Closed rectangular container with a square base is to have a volume of 2250 inches cubed. Material for the top and bottom of the container costs $2 per foot. Material for the sides will cost $3 per foot per square inch. Find the dimensions of cost of the container of least cost. So closed rectangular container with a square base. So it's got a square base and it's a container. Right? So I'm going to call the sides X and then the height H. Now, on the side, they cost $3 per square inch, and the top and the bottom is cheaper, I guess. It's $2 per square inch. Okay. The cost function, we're trying to get least cost, so we need a cost function. Well, the area of the top and bottom, there's two of them, are both x squared times the price of $2 per foot. The sides, there's four of them. They're each xh, and their cost is $3 per square inch. So our cost function is 4x squared plus 12xh. Now we probably want it in terms of one variable, so that's where there's a required volume. Volume equals length times width times height. And so the length is x, the width is x, the height is h, so x squared h, and it should equal 2250 cubic inches. So now we can solve for x or h. I think it's going to be easier to solve for h. So I'm going to divide by x squared to get my h, and then plug that into that equation. So I'm going to get my cost function in terms of one variable. So the cost function is 4x squared plus 12 times, that seems like a big number, 12 times 2250. 0, 10, carry the 1, 4 is 5, 4, 0, 0, 5, 2, 2, 0, 0, 10, carry the 1 to 6 is 7. 27,000 over x is my cost function in one variable. Okay, that's fine. So let's take the derivative. C prime equals 8x. Now I don't want to do quotient rule on this. I'm going to think of it as x and negative 1. So it's going to be minus 27,000 x and negative 2. So that's going to be 8x minus 27,000 over x squared equals 0 undefined. I'm going to combine these into a single fraction. If you cross multiply, you're going to lose critical points. So I'm going to multiply top and bottom of this by x squared. So C prime equals 8x cubed minus 27,000 over x squared equals 0 undefined. So undefined comes from this guy on the bottom, which is a bounce. 0 comes from the top. X cubed equals 27,000 over 8. And take the cube root of both sides. No plus or minus. It's an odd root. The bottom works out pretty nice. It's just 2. Now, what can we take out of this? 27 times 1,000. Now, 1,000 is 10 times 100. It's 10 times 10. There's a perfect cube right there. And this is actually 3 cubed. So we get a 3 and 10, we get 30. The answer is actually 15. Worked out really nice. Okay, so that's a critical point. Endpoints. Smallest x to be, x cannot be 0. Because then you don't have the volume of 2250 inside. And as h goes to 0, x squared x blows up, goes to infinity. So we don't have endpoints. We could do kind of an EVT style thing. We make like a table and we plug it into the cost function. 4x squared plus 12x 2250 over x squared. So we can say limit as x goes to 0. We get 15, and the limit as x goes to infinity. So as x goes to 0, this term goes to 0. This one blows up and goes to positive infinity. As limit goes to infinity, that one goes to 0, and that one blows up, so it goes to positive infinity. If you plug 15 in, you're going to get what's 15 squared? 225. 25 gives you 7, 0, 1, 5, 1, 225. So it's going to be 225 times 4, which is 450, which is 900, plus 12 times 2250 over 15. Divided 3 out of this, 3 out of this. 5 goes into this. Well, every 250 is 55s. I don't know. I can't do math right now. 2250. I'm giving up trying to do it in my head. So that's going to be 4. That's going to be 5. That's going to be 0. 450. 450? 450 times 4 is 900. 1800. The answer is 2,700. 27,000. Is that all right? No. I think it's 450, 900, 1800. It's 2,700. I think it's 2,700. Okay, so I mean, clearly this is the min because it blows up as you go to these other extreme cases, but it's hard to defend that. So we could do a first derivative test and say, okay, let's do C prime. Let's put 15 on there. Let's test a point. x equals, where's c prime at? X equals, I want to say just put 1 in there or something. If we put 1 in there, it's definitely negative. Negative, positive, decreasing, increasing, relative min. But then, of course, it's going to be an absolute min this time. So the answer is, now, if you want to find the absolute min, you still got to do this calculation. Even if you take this approach, you got to plug this back in the original. So, I mean, it just said find the dimensions of the least cost. It didn't say find the least cost. So if you take this approach, it might be worth it not to go through all that extra effort to find it. If you're doing a table, you're already doing it. But the minimum cost is $2,700 when the sides of the base are 15 inches and the height is this h right here, right? I mean, we could plug it in here too. It's gonna be 2250 divided by x squared, 15 and 15, which is 225. So I think it's 10. Height is 10 inches. So we got to say, since there is a relative minimum here by the first derivative test, for relative extrema, you got to explain how it works. Since c prime is negative on negative infinity to 15, and c prime is positive on the interval 15 to positive infinity. And since it is the only relative extrema, blah, 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 you can look at my solutions. It's got to be the absolute minimum. So, okay, a couple more. So commercial cattle property currently allows 20 steers per acre of grazing land. On average, its steers weigh 2,000 pounds on market estimates. The agricultural department indicate that the average market weight per steer will be reduced by 50 pounds for each additional steer added per acre of grazing land. How many steers per acre should be allowed in order for the ranch to get the largest possible total market weight for its cows? So total market weight, I'm going to call it W, is the weight per steer, weight of one steer, times the number of steer, right? The weight of one steer, we're going to say starts at 2,000 and then minus 50 times how many additional steer we add. The number of steer starts at 20 and then we add to that or take away. This is going to be 4 with 4 zeros, 1, 2, 3, 4, plus 2000x minus 10 with 2 more zeros, x minus 50x squared. So we could say 40,000 plus 1,000x minus 50x squared. So W prime equals 1,000 minus 100x. You said equals 0 undefined. X equals 10 is your critical point. Your endpoints are, technically we could take away 20 steers because there are 20. Can't go to negative steers total. And the most we could add would be when their weight gets to 0, it doesn't make sense to add more. So the weight, when the weight's 0, That of one steer, that'd be 2,000 minus 50x. So 50x equals 2,000 divided by 50. That's going to be 40. 40 is the most you can add because otherwise they're going to have negative weights. So those are your endpoints. We're going to create a table. It looks like we're going to be able to use extreme value theorem, which hopefully by now you're convinced is the easier way to go. We have our formula here, original formula before we take the derivative. We're going to add it in. So if you put negative 20 in here, I think that, well, let's see. That would be, that'd be 1,000. But then that would be 0 and you're going to get 0 because you took away all the steer. So they don't weigh anything if there's none. This is going to be 2,000 minus 500. And this is going to be 30. So that's going to be 1,500 times 30. It's going to be 45 with 3 zeros. If we do 40, that's going to give you 0 here, 60 here, and you're going to have 0. So this is your max. And so now we just need to write that as an answer. Now you could do first derivative test, but explaining it sucks. Don't do that. I'm going to expect you to explain it if you do it that way. Don't do it unless you have to. The maximum total weight is 45,000 pounds when 30 steer, 30 steer because it's 10, but we add 10 to 20. 30 steer per acre are allowed by extreme value theorem. Checking endpoints and critical points. You just that. All right, last one. Figure shows offshore oil well located at point W. That is 5 kilometers from the closest point A. A straight shoreline oil is piped from W to shore point B. That is 8 kilometers from point A by piping it into a straight shore between A and B, then B via pipeline. It is if the cost of laying pipe is $1 million per kilometer underwater and $500,000 per kilometer on land. It's cheaper on land. We want to minimize the cost. Okay, this is where we should put x. That's 5. This is going to be square root of x squared plus 25. This is going to be 8 minus x. Okay, now these numbers are really big, so I'm tempted to maybe just say, let's do hundreds of thousands. So this is 5 hundreds of thousands. This is 10 hundreds of thousands. And my final answer should bring that back, but for now I'm just going to use 5 and 10. You don't have to do that. The cost is price per item times number of items, right? So this is going to be 10 times the square root of x squared plus 25. And this is going to be 5 times 8 minus x. Now, some people make the mistake. They try and treat this like a time problem just because, like, well, every time I've done a problem like this, it was time. Well, this isn't time. Think, stop, think, please. So we have 10 square root of x squared plus 25 plus 40 minus 5x. It's already in one variable. We want to take the derivative. So that's going to be 5 x squared plus 25 to the negative 1/2 times the derivative of what's inside is 2x minus 5 equals 0 undefined. So C prime equals, this is going to be 10x over the square root of x squared plus 25 minus 5. We want to give these guys a least common denominator. So it's going to be 10x minus 5 square root of x squared plus 25 over the square root of x squared plus 25 equals 0 undefined. Undefined comes from the denominator, which gives you plus or minus 5i, which we're going to throw out. 0 comes from the top, so that's going to be 10x equals 5 square root of x squared plus 25. We could divide a 5 out of both sides. That would make life a little easier. And then square, I'll just rewrite it real quick. And then square both sides. You get 4x squared equals x squared plus 25. So then we get 3x squared. And we get x squared equals 25 over 3. So we're going to take the square root of both sides, plus or minus. I'm trying to finish up early. And just 2 minutes left. 5 over root 3, plus or minus. These are your critical points. Your endpoints are x could be 0. It's not going to be negative. And it could go up to 8. So now we need a table. Plug it into your cost function. So we're going to do negative 5 over root 3, 0, 5 over root 3, and 8. I'm not going to do that one. If you plug 0 in, you get 50 plus 40 equals 90. If you plug 8 in, you get 10 times the square root, 64, 89 plus 0. And that's about 9.5, maybe 95. If you plug 5 over root 3, that's going to be 25 ninths plus 25 over 1 plus 5 over, this one's a little grosser. Now I'm just going to cut to the chase. There's a little more detail work to show, but this answer right here with a calculator comes out to, it's going to be end up 8,330,127.0193 decimal accuracy. This one is 9, because these are hundreds of thousands, so it's actually 9.4 million, 9433981.132. This is your max. This is your min. We're looking for the min. So here's your min. You still got to write an answer for it and justify it, but I'm going to stop my video right now because otherwise it might get sabotaged because I waited too long.